Hello, I'm Konstantin and I'm going to talk about universally robust information aggregation for binary decisions. This is a joint work with Itai Arieli, Yakov Babichenko, and Inbal Talgam-Cohen. We'll start with a motivating example, then we'll briefly describe our main results. We'll proceed by presenting the formal mathematical setting and two complementary approaches for tackling the problem. Finally, we'll briefly discuss related work and make some points for future research. As a motivating example, let's think of a decision maker, such as a politician, who considers implementing some public project. But unfortunately, she doesn't know whether the project will be beneficial or detrimental to the public. So there is some state specifying whether the project is beneficial or detrimental. But the decision maker doesn't know the state. Rather, she only knows some prior distribution on the values of this state. To improve the decision-making process, she conducts a binary answer anonymous survey among several agents, which we assume to be just ordinary members of the public. And we consider a common interest scenario, meaning that the decision maker and all the agents have the same utility function. One possible justification for this assumption is that the decision maker is a honest public servant, but in hindsight, we will see another justification that is arguably more convincing. In our model, each agent has some private information about the state, and we impose a symmetry assumption, meaning that the private information of different agents is drawn from the same distribution. And we assume that this marginal distribution is known both to the decision maker and to all the agents. Since the scenario is common interest, we assume that the agents are truthful, meaning that an agent recommends implementing the project if and only if, given the prior distribution and her private signal, she believes that the project is more likely to be beneficial than detrimental. And since the decision maker conducts an anonymous survey, she only observes the statistics of the recommendations. There is a catch. We assume that the correlations between the private information of different agents are chosen by an adversary. And therefore, the decision maker aims to aggregate the information robustly well. And please know that we consider a single-shot game, meaning that there is just one iteration. But what do I mean by aggregating information robustly well? Because, of course, there are multiple robustness paradigms. So the arguably simplest robustness paradigm is the minimax approach, under which the decision maker just tries to maximize the expected probability of a correct guess for the worst possible choice of correlations by the adversary. But in the symmetric setting we consider, this approach turns out to be rather straightforward. Indeed, it is pretty straightforward to see that the best strategy for the adversary is just to fully correlate the signals, because it would reveal the minimal possible amount of information to the decision maker, and essentially it will reduce the problem to a single agent setting. And what would be the best reply of the decision maker? Intuitively, since the setting is essentially single agent, the decision maker should just follow the recommendation of one specific agent. But we should be careful here because the setting is anonymous, and therefore the analog of this behavior in the anonymous setting is what is known in the literature as the random dictator aggregation rule, meaning that a decision maker picks one agent uniformly at random and follows her recommendation. But there are also more sophisticated robustness paradigms that involve a benchmark of a hypothetical Bayesian decision maker who knows the correlations between the private signals of the agent. And we can either compare the performance of the aggregation rule chosen by the actual decision maker to the hypothetical benchmark additively, which we call regret minimization, or multiplicatively, which is known as approximation ratio. Now let's briefly describe our main results. First of all, we prove that when the number of agents is large enough, then all three robustness paradigms, minimax, regret, and approximation ratio, are equivalent. And moreover, the unique asymptotically optimal aggregation rule is random dictator, regardless of the chosen robustness paradigm. This equivalence fails to be true for a small number of agents. However, we still manage to characterize the minimal regret for any number of agents via the concavification of the probability of a correct guess by the hypothetical Bayesian decision maker. And this result is a bit surprising because it expresses the guarantees of the ignorant decision maker through the utility of the hypothetical Bayesian decision maker. Now let's present the formal mathematical model. And to keep the presentation simple, we'll consider a simplified version of it, but many assumptions that you can think of them as limiting can actually be relaxed. And moreover, we'll only focus on regret minimization. So let's assume that there are just two states, 0 and 1, and denote by omega the true state. Let's further denote the prior probability for the state to be 1 by mu. The setting consists of a single decision maker and n truthful agents. And let's assume that each agent can just get one of two possible private signals, the low signal L and the high signal H. We denote by Si the private signal of agent number I. And the decision maker aims to guess the state correctly. But in the paper, we show that the results hold for any number of states, as well as for any number of signals. And moreover, the utility function of the decision maker can actually be arbitrary. An important notion in the model is information structure. The information structure specifies for each state with each probability, each possible profile of the signals for all the agents is reduced. And we assume that the marginal information structure, meaning the distribution of signals for each state for a specific agent, is fixed and is the same for all the agents. Moreover, it is known both to the agents and to the decision maker. And in particular, since the marginal information structures are known to the agents, when an agent gets a private signal, she updates her belief about distribution of the state to a posterior belief using Bayes' law. The adversary can choose any information structure she wishes, with the only restriction being that it must be consistent with the fixed marginal information structures. Now let's consider the point of view of some specific agent. We denote her posterior probability for the state being 1 upon observing the low signal by P1, and upon observing the high signal by P2. And we assume that P1 is smaller than 1/2, while P2 is higher than 1/2. And this assumption is reasonable because if, for example, both posteriors are weakly below 1/2, then each agent, regardless of the private signal, will always recommend to guess that the state is 0. And therefore, the decision maker can safely ignore the signals as well. And the problem is degenerate. We assume that each agent makes an anonymous binary report where we interpret 0 as recommending to guess that the state is 0, and 1 as recommending to guess that the state is 1. And since the reports are anonymous, the decision maker only observes what we call empirical posterior, which is the fraction of the agents who recommend guessing that the state is 1. The decision maker aims to guess the state, but she is also allowed to use mixed strategies, and we capture it by what we call an aggregation rule. An aggregation rule is a mapping from the empirical posterior to the probability that the decision maker guesses that the state is 1. In our paper, we show that the assumption that the reports are anonymous is a fallacy of generality, and it can be dropped. I remind you that the decision maker in our model doesn't know the information structure, and the benchmark is a hypothetical decision maker, which we call Bayesian, who knows the information structure. For any aggregation rule F, we denote by the regret of F the maximum possible difference between the probabilities of the correct guesses of the actual decision maker and the hypothetical Bayesian decision maker, where the maximum is evaluated over all possible information structures. And I remind you that we focus on a one-shot gain, meaning that there's just one iteration. And the decision maker aims to pick an aggregation rule that would minimize the regret. Now let's present the first main result, and to this end, I need to remind you of the notion of concavification. Given a function h, its concavification, denoted by cav h, is the pointwise smallest function, which is concave, and it is never below the function h. For example, for the yellow function in this diagram, the concavification is the green function because it is concave and it is the pointwise smallest concave function that is never below the yellow function. Let's think of the probability that the maker guesses the state correctly as being a function of the information structure. And the question is, how many variables does this function get as input? And the answer is 2 to the n plus 1, where n is the number of agents. Why? Because there are two states, and for each state, there are 2 to the n possibilities for the vectors of the private signals of all the agents taken together. And our first main result says that the minimal regret always equals the maximum possible distance, difference, between the probability of a correct guess of the hypothetical Bayesian decision maker and its concavification, where the maximum is taken over all possible information structures. And even though this function representing the probability of correct guess of the Bayesian decision maker is high dimensional, we still can use this result with some modifications to compute the regret for small numbers of agents and even find the optimal aggregation rules. But unfortunately, it turns out that even just for 2 agents, the analysis is complicated. And moreover, the optimal aggregation rule needs not to be unique. However, as our second main result shows, these weird phenomena are eliminated when the number of agents grows larger. So let's state our second main result, which is for any given prior distribution and the marginal posterior distributions, when the number of agents is large enough, then the unique regret minimizing aggregation rule is random dictator. And moreover, this result also holds for approximation ratio greater than regret. Note that this result also justifies in hindsight the assumption that the agents are truthful, because in random dictator, we either ignore totally the recommendation of some agent or adapt it as is, and therefore there is no incentive to misreport. Now let's briefly discuss related work, and there is a wide literature on forecast aggregation, which is a bit different from our setting, because in forecast aggregation, the agents submit their private recommendation, which may have many values, but in our paper, each agent just submits a binary recommendation. But we'll only discuss in details the most closely related paper to ours, which is the paper by the Oliveira, Ishii, and Lin. Their model is very similar to ours. Their advantage compared to us is that they don't impose the symmetry assumption on the agents, but on the negative side, they only consider the minimax robustness paradigm. They prove that the optimal aggregation rule under the minimax paradigm is to adopt the recommendation of the best agent, where the best means the one who has the most informative private signal. And the obvious analog of following the best agent in our anonymized symmetric setting is random dictator, because all the agents are equally good. And therefore, our asymptotic result on the universal optimality of random dictator can be viewed as a natural extension of the result of the Oliveira, Ishii, and Lin on the optimality of following the best agent under the minimax paradigm. Let's sum up. We initiate the study of regret minimization over symmetric aggregated information. We prove that when the number of agents is large, then regardless of the robustness paradigm, the only optimal aggregation rule is random dictator. This result is not true for a small number of agents, but still for any number of agents, we characterize the optimal regret of the ignorant decision maker, a bit surprisingly, through the guarantees of the hypothetical Bayesian decision maker. There are many natural questions for the future research, and one especially interesting question is, are there some benign limitations on the power of the adversary under which a more natural aggregation rule such as supermajority would perform better than random dictator? Because the random dictator is essentially performing no aggregation, and therefore we can view our asymptotic result as a negative one. And of course, one can ask what happens if the agents are not restricted to binary reports. And of course, instead of considering one-shot games, we can switch to an online setting and ask how can the decision maker learn to minimize regret. Thank you very much for your attention.